Let's work through two example problems with a linear drag force. So scenario number one, suppose we have a box here on some frictionless surface. We give it an initial velocity to the right, and although there's no friction, there is going to be an air drag on it, slowing it down over time. We call it a linear drag force if it depends linearly on the speed v of our box. Okay, we'll have our free body diagram here. There's nothing important going on in the vertical direction, and there's just that air drag force in the x direction, because again, no friction in this case. So Newton's second law, here is our drag force, and that minus sign right there is the indicator that our force is acting like a drag. It's opposite whatever our velocity is. So v is our velocity, and our force is opposite the velocity. So if our velocity is positive, the force is going to be negative, and vice versa. So we can rearrange this into an integral that we can solve. The key move in our analysis is taking this velocity dependence here and packaging it with the dv down there. So I'm going to divide the whole thing through by velocity, so we get dv over v on the left-hand side. And we're left with this on the right-hand side here. So we're going to integrate both sides, make sure our limits match up. So at time 0, we have some initial velocity v0, and we're going to some future time t, where we'll have some future velocity v of t. And that's what we're trying to get, this velocity function, to see how exactly with time this box slows down in the presence of this linear drag force. Okay, so we have our antiderivatives here, and note that on the right-hand side, we've got a time constant. We can tell that because on the left-hand side, we've got a velocity over a velocity, so that's dimensionless. Therefore, the right-hand side must be dimensionless. So if this is a time here, then mass over this constant b must also be a time. B is just some constant here. We haven't specified anything else about it besides that it's a positive constant. But we can tell here that m over b must be equal to a time, so we have a time constant tau, m over b. And that gets us to our exponential decay for our velocity. Graphing that, velocity versus time, we start at some initial velocity here, and we see that it's going to take forever for this box to come to rest. That's characteristic of a linear drag force. We get these exponential decay functions. So it slows down, never gets fully to rest, but that time constant tau characterizes the relative amount of time it takes to slow down. In particular, tau is about the amount of time it's going to take to drop to a third of its initial speed. How far will it go? We can find that as well. It's going to take forever to fully come to rest, but will it drift an infinite distance in that time? Well, we can find out. We know that our velocity here is dx dt. So just replace that with dx dt, and we can integrate again. So integrating dx, integrating this function here, and that gets us to that function. And so graphing position versus time, we start here at this initial position, and we see that we're going to be asymptotically approaching some final position here. And the distance that we've traveled, our final distance, when t goes to infinity, let's see, t goes to infinity, e to minus infinity is 0, so 1 minus 0 is 1. So our final displacement will be v naught times our time constant tau, or v naught m over b. That distance there will be the displacement that we approach as time goes to infinity. So we don't travel an infinite distance, we travel this distance right here. It's going to take an infinite amount of time to reach that location, to actually travel that distance, but it is a finite total amount of distance that we travel when we are slowing down subject to a linear drag force. Okay, that's scenario one. Next one to look at. A skydiver type scenario. Suppose this time we're released from rest and allowed to fall. And while falling, we're subject to a linear drag force. The air drag will increase in magnitude as our speed increases. So here's our little FBD at some point while falling, gravity pulling down, so a constant force of gravity down, and some variable drag force pointing up. The drag force is going to be small at first when our v is small, but it's going to be getting bigger over time. Let's orient our axes so that y points in the direction that we're moving. So we have a positive velocity. That'll be convenient. So we're moving in the positive direction. So y is down. Go to Newton's second law, dv dt. Here's our sum of forces. Gravity in the plus y direction, drag force in the minus y direction. That's that minus sign right there. And then here is our drag force, minus CV, our linear drag force. When I started writing this problem, I initially had a nonlinear drag force here, and I changed my mind to make it a linear drag force. That's why I got all these crossouts everywhere. This is just some constant here. The C is just some constant. So here's our linear drag force and our constant force of gravity pulling us forward. Okay, so we're going to want to integrate here, and I recommend before moving this v down underneath the dv over here, we clean things up a bit by factoring off the coefficients in front of v. So if I factor out a minus c over m from this whole thing, then this, here's our n2l, cleaned up, it becomes this right here. Factor out the minus c over m times v minus mg over c. So check my algebra there. I think that gets us here. And now at this point, here's where we make our move. And we're going to divide both sides by the function that involves our velocity. I want to get this whole thing underneath the dv. So here's our velocity function that I want to get underneath the dv. So that's this step right here. dv divided by our velocity function, and then move our dt up over to the right-hand side. So minus c over m times dt. We can tell right here that we've got another time constant. Since this is a velocity, and a velocity, dimensionless on this side, must be dimensionless on this side. So m over c, that's going to be our time constant this time. All right, integrate both sides. Make sure our limits match up. We had initial time 0. We have velocity of 0. Since this time we're starting from rest, we're dropping from rest. And we're going to some future velocity v at some future time t. Okay, find your antiderivative, apply your limits. The right-hand side is easy. That just gets us a minus t over tau. And we end up here once we finally solve for v of t. Rearrange, and we get this exponential decay function that's flipped and shifted up. So if we plot velocity versus time, we start at rest, and we're gradually speeding up, but we don't speed up forever. In fact, we're asymptotically approaching some final velocity. As time goes to infinity, we're getting closer and closer to this velocity right here. Time goes to infinity, e to the minus infinity is 0, 1 minus 0 is 1. So this is the final velocity that we're approaching. In fact, that's our terminal velocity, mg over c. So that constant c determines or has an effect on the terminal velocity that we eventually reach. But we could have predicted that this would be our terminal velocity without actually solving the differential equation. We could have gone all the way back here just to n2l and looked here. We can tell that as we're falling, v is getting bigger and bigger. So there'll be a point at which CV becomes as big as mg. And when those are equal, the net force is 0, meaning our acceleration is 0, meaning our speed isn't changing anymore. So we've reached our terminal velocity when our acceleration goes to 0. So the point at which these two terms balance, that's when we've hit terminal velocity. So setting mg equal to cv, we could have solved for the terminal velocity way back here to find that it's mg divided by c. And our calculus here confirms that.